Close your eyes and settle in. Tonight, we are going to talk plainly about an interstellar comet passing the neighborhood of Mars. The object is called 3I, with the I meaning interstellar, and the discoverer's tag, Atlas, attached to its name. It is not bound to our sun. Its path is open, hyperbolic, and after it sweeps through, it will keep going back into deep space. There is no danger in this story, no impact, no dust storm, no change to Mars's thin air. There is only an opportunity to measure a visitor from another star system with instruments that already circle the red planet. Picture the basics. Sunlight warms the surface of the nucleus, ice turns to gas, gas drags dust. The cloud around the nucleus is the coma, and the long, faint extension is the tail. That is standard comet behavior. Interstellar origin does not change the physics of sunlight and ice. It simply means the material formed under a different star and carries a different history. From a distance, 3I Atlas acts like a comet we understand. Up close, its exact mix of gases and grains is the part we want to learn. Now, anchor the geometry. Near Mars, in astronomy, still means very far. The separation is measured in tens of millions of kilometers. At that range, the coma is a gentle glow in a telescope, not a physical presence at the planet. For a meteor shower to occur at Mars, dust would have to cross the atmosphere. That is not happening. For a chemical change to occur, gas would have to reach the air in measurable amounts. That is not happening either. Mars orbiters remain safe. Mission teams will simply point cameras and spectrometers toward the comet during planned windows and then return to their normal routines. Why point from Mars at all if Earth can observe too? Because angles matter. The way dust scatters light depends on the angle between the sun, the comet, and the observer. From Mars, that angle is different than it is from Earth. Different angle means different sensitivity to fine grains, jet structure, and subtle brightness changes. Another advantage is cadence. An orbiter can take many short looks across a Martian day without weather and without the same day-night interruptions we have on Earth. String those looks together and you get a clean time series right when the comet's activity is changing most quickly. What can instruments measure, even if they were designed for Mars? Cameras deliver photometry, carefully calibrated brightness as a function of time. Spectrometers split light by wavelength and reveal gas lines from familiar species such as water, carbon dioxide, and carbon monoxide, along with simple radicals formed when sunlight breaks molecules apart. Filters isolate dust continuum so teams can separate it from gas emission. Navigation cameras and even star trackers add extra data points when science cameras are busy. Radio tracking and timing improve the orbit solution by tightening the fit to where the comet actually appears in the sky. Those measurements translate into specific quantities. A brightness curve tells you if the nucleus is rotating and whether active vents brighten and fade as they swing in and out of view. Abrupt steps in the curve point to outbursts when a patch of crust breaks and fresh ice vents quickly. Spectra become production rates, molecules per second leaving the surface. Compare species and you learn which ices dominate and how the balance shifts as the comet warms. Imaging of the coma and tail constrains dust size. Very fine grains are pushed strongly by sunlight and spread into broad, smooth shapes. Larger clumps stay more collimated and create narrow fans and striae. Precise positions across many images reveal tiny, non-gravitational accelerations, the small net push from asymmetrically venting jets. Combine all of this and you infer rotation period, gas production, dust-to-gas mass ratio, jet geometry, and limits on the mass and density of the nucleus. It also helps to be clear about what is not occurring. There will be no comet-driven meteor shower at Mars. The dust is not intersecting the atmosphere. There will be no noticeable change in atmospheric chemistry or pressure. The coma is far away and extremely tenuous. Orbital debris risk does not increase. Spacecraft do not need shielding maneuvers or safe modes. The only things reaching Mars are photons, And those photons are valuable because they carry information about composition, temperature, and structure in the comet itself. Context makes the event meaningful. The first interstellar visitor we saw, 1I Oumuamua, looked like a bare body without an obvious coma and produced puzzling small accelerations. The second Tusai Borisov behaved like a classic comet with abundant gas and dust. A third sample matters. If 3I Atlas shows a typical volatile mix and ordinary dust sizes, that supports the idea that protoplanetary disks produce broadly similar small bodies across many stars. If it differs strongly, say with unusual gas ratios or grain properties, then we have evidence of different temperatures, pressures, or chemistry where it formed. Either outcome teaches us something real. From Mars, two strengths stand out again and again: geometry and cadence. A different Sun-Comet observer angle sharpens sensitivity to forward scattered light, which enhances faint structures and reveals tiny grains that are otherwise hard to detect. High cadence turns scattered snapshots into a coherent story. You can watch the coma breathe as vents change output. You can catch a short-lived outburst instead of hearing about it after it fades. And you can correlate changes in brightness with changes in specific gas lines. That correlation is the key to tying what you see to what the nucleus is doing. Turning raw images into physics is careful work. Each frame is calibrated for instrument bias and thermal noise. Flat field corrections remove pixel-to-pixel variations. Background stars are used to register the scene and to convert counts into actual brightness. For spectra, the instrument response is removed and the solar spectrum is accounted for, so gas lines can be fit with models that include how quickly each species is created and destroyed in sunlight. For astrometry, the measured center of the coma is tracked across time and compared to the orbit predicted by gravity alone, with a small term allowed to capture jet thrust if needed. In the end, every number has an uncertainty bar. Those bars matter as much as the values. What outcomes would be especially interesting? A high carbon dioxide to water ratio would imply formation in a region colder than typical for many inner system comets. A strong dust signal with weak gas would suggest crusty surfaces that shed grains easily or icy material hidden beneath a mantle. A very small, non-gravitational term, despite active outgassing, would hint at either a large, heavy nucleus or jets aligned in such a way that their pushes cancel. An unusually fast rotation would stress the body and raise the chance of surface shedding. Any fragmentation event would open a short window to probe internal strength and the layering of ice and dust. If you follow public releases, look for three simple plots that tend to appear. One plot shows brightness versus time. Smooth waves suggest rotation. Sudden steps indicate outbursts. A second plot shows production rates of at least two key molecules over time. If they rise and fall together, the heating is opening broad areas. If one leads the other, layered ices are being exposed at different depths. A third plot shows tail direction, or length, versus time. As grains are accelerated by sunlight and shaped by the solar wind, that direction shifts in predictable ways, and the pattern tells you grain size and ejection speed. Small residuals in the orbit fit mean the geometry is well understood. Persistent, tiny deviations mean the jets are exerting a steady, measurable push. Keep expectations simple. The past is quiet. The science is specific. Mars is a convenient second observatory that sees the same object from a different angle and at a steadier cadence. The result is not a dramatic scene in the Martian sky. It is a cleaner, richer data set. Those data feed models of how small icy bodies warm, vent, shed, and evolve, and they add a measured point to a very small but growing catalogue of interstellar visitors. As you drift towards sleep, hold the essentials in order. An interstellar comet is passing safely by Mars. It behaves like a comet. Sunlight warms it. Gas escapes. Dust follows, a coma glows, and a tail points away from the sun. Nothing reaches Mars. Spacecraft look, record, and compare. From brightness, we learn rotation, and activity. From spectra, we learn which ices dominate. From images, we learn how dust grains are sized and released. From precise positions, we learn how jets nudge the nucleus and how massive and cohesive it might be. Each piece supports the others. And remember, the larger meaning. One object is a curiosity. Two become a comparison. Three begins a pattern. With each additional interstellar visitor, the picture of how other planetary systems build and scatter their small bodies comes into clearer focus. We do not need dramatic events to learn. We need careful measurements, steady cadence, and honest interpretation. That is what Mars can give us this time. A quiet vantage point, a different angle, and the patience to turn faint light into reliable facts. Breathe slowly. The red planet continues its orbit untroubled. The comet continues its passage unbound. Instruments click and hum, gathering photons that have crossed cold space to carry information from ice and dust older than our seas. No alarms, no rush, only the slow work of seeing clearly. And that is enough.